So welcome back. This is part 2 of lecture 26, and my goal in this part is to just give you some examples of inner product spaces. Okay, so kind of the example that you should kind of always think of at the beginning is something that you already saw in first year, which is the dot product, right? So we introduced the dot product at the very beginning of today's lecture in the first part, and the dot product in Rn is an example of an inner product. Okay, so you could think of the inner product, the vectors u and v, is defined to be u1 times v1 plus the second coordinate of u times the second coordinate of v up to u and vn. Right, so normally we denoted this as the dot product u dot v, but we can think of it as what this is doing is taking a pair of vectors and mapping it to a number, and it's mapping it to this particular number. And this operation satisfies all the properties that are listed here about positivity, definiteness, addition, and so on. If you actually pull out your Math 1 BO3 textbook, you will find all of these properties proved for the dot product. Okay. Now, more generally, we can define what's called the Euclidean inner product on Fn. And the way that this is done is take two vectors in Fn, right? So this is my first vector, here's my second vector, and I've written it out so you can see the various coordinates. And the way that this is defined is taking u1 times the conjugate of v1 plus u2 times the conjugate of v2 and so on, all the way down. Okay, and so the important thing to notice here, though, is that if the field here F is R, then all of these numbers that I'm taking the complex conjugate is just going to be the number V, the VI's to begin with, because you're taking conjugates of real numbers. So if F is R, then this is the same definition as example 1. So what you were learning in Math 1 BO3, we called it the dot product, but kind of a more formal name is it's actually the Euclidean inner product on Rn. That's another way of thinking about it. Okay, but we want to move on to kind of some more, let's call them exotic inner products. Okay, and here's kind of an inner product that uses a lot of calculus. Okay, so here, let's take two polynomials where their coefficients are real numbers, and we're going to associate to p and q, right? So these are polynomials. We need to associate to it a real number. And the way that we're going to do that is we're going to integrate on the interval from -1 to 1 by which polynomial. We're going to take these two polynomials p and q, multiply them together, and then integrate them from the interval from -1 to 1. So this is a polynomial. You can integrate and evaluate it from -1 to 1. There won't be any discontinuity, so this will be defined and you'll get a real number, right? That's what you would have learned from calculus. And the interesting thing is, this operation, which takes these pair of polynomials and associates it to a number, actually satisfies all the conditions for being an inner product. Right? Now, some of it we can't prove all the details, but because this isn't really a calculus class or analysis, but I can sketch out kind of why it's true. First of all, let's look at a single polynomial and take the inner product of that polynomial with itself. So that means I have px times px, right? So I have px squared. And this is always going to be bigger than or equal to 0. All right? So since px squared is greater than or equal to 0, for all x. Okay, so you kind of want to try to visualize what this is. What this means is when you graph this function px squared, it's always above the y-axis. So that means the area from -1 to 1 has to be positive. Okay, so i.e. the area under px squared is positive on the interval -1 to 1. Okay, so think about it in terms geometrically. Now, the second condition says that the inner product, we're interested in when is this inner product of p with itself is 0. Well, that would mean that this polynomial here, or this, sorry, not this polynomial, this integral right here is 0. And this can only happen if and only if the polynomial is the 0 polynomial. Okay, and now this equality here kind of requires some real analysis. Right? But just take it as a statement of faith that the only way that this polynomial, this integral can be 0 is if the polynomial was 0 to begin with. Okay. Now let's look at some of the other properties. Okay. So the next property was kind of, additivity in the first slot. So I have two polynomials, p plus q, and I'm going to do the inner product with r. So I'm just following the definition. This is what goes in the first slot. This is in the second slot. And I can expand this out. Okay, so I'm taking the integral of this polynomial on this interval. But notice that I can break it up from what you know from calculus, right? That this is the same as the integral from -1 to 1 of this polynomial plus the integral of this polynomial on the same interval, right? And so this looks like a property from calculus. And now when you stare at what these guys are, well, that's just equal to the inner product of p and r. That's the first term. And this guy here is the inner product of q and r, which is the second term. So we do have the homogeneity, the additivity in the first slot. The homogeneity, the proof is very similar. I start with this lambda times p and q. I plug it, use the definition, and then from calculus I know that I can factor out a constant when I'm doing integrals. And notice that this is the same thing as lambda plus the times the inner product of p and q. So we have the homogeneity in the first slot. And then what we have, we want to show that because we're doing the vector space over real numbers, all we need to do is show that we can swap the order around, right? So we take p and q, we apply the definition, but you know from calculus that it doesn't matter which way you put the product of polynomials when you're integrating. And this is the same thing as the inner product of q and p. Okay, so keep this example in mind. We're going to kind of use this particular example of an inner product to kind of come up with examples of more exotic examples, okay, and more complicated ones that you would have seen. So that's all I wanted to kind of do in this part. In the next part, I want to introduce inner product spaces.